All right, recording is on. Arvind, thank you so much for coming. Also, let me just introduce you. I'm sorry for the way how I pronounce your last name. I'll do my best. So everybody would like to introduce you to Arvind Raghunathan. So Arvind, he's an expert in nonlinear optimization, multiple areas of nonlinear optimizations. He did his PhD at Carnegie Mellon University, and now he's a senior principal research scientist in the data analytics group at Mitsubishi Electric Research Laboratories. So he works in a lot of practical applications at the same time, develops really state-of-the-art theory in nonlinear optimization, and we are very excited to hear his work in the decision diagrams here. So Arvind, take it away. You're muted. I think you're just muted, Arvind. Yeah.
Oh, can you hear me now?
Yes, that's perfect.
Okay, all right. Let me just hide this. Okay, all right. Thanks very much, Andre, for the invitation to the Winter School on Decision Diagrams. I do remember the meeting a few years back, and I'm happy that you invited me back for the Decision Diagrams meeting. And like Andre said, my interests lie in the intersection of continuous and discrete optimization. And this particular work is related to global optimization of mixed integer nonlinear programs, right? This is joint work with Carlos Nora, who was a postdoc with me at Mitsubishi Electric Research Labs, and also with Carlos Cardonia and David Bergman at University of Connecticut. So the focus of this talk is on multilinear programs, MLPs. Right? By MLPs, we refer to programs of the following form, where we're minimizing a scalar objective function subject to a set of constraints, where the variables x, a vector of variables x, belong to a compact set. So they could be continuous, they could be binary, integer valued, and so on. It's just that we require that these variables lie in a bounded set. The functions fk essentially have the following form, where they are a linear combination of monomials, where these monomials fk high take the following form, where you have this vector x raised to the power dki, and this is essentially equivalent to some product of a subset of the variables in your optimization problem. Okay, that's essentially a multilinear term, and every function that we have is a sum of such multilinear terms, and this is what we refer to as a multilinear program. Now, for the rest of the talk, just for sake of simplicity, we will ignore the constraints in the MLPs. However, the techniques that we describe can be easily applied and extended to the case of constrained MLPs as well. So for the rest of this talk, we are going to be looking at the following setting. We're going to be minimizing a scalar objective function, which we call f of x, subject to x lying in this compact set. And this f of x is now a linear combination of monomials f sub I of x, where each of these f sub I of x are essentially a product of a subset of the variables. And this d sub I is essentially an indicator function having a 0 or 1, suggesting whether the particular variable xj figures in this multilinear term or not. Right? Right. Now, where do these multilinear functions actually occur? Right? I mean, these functions occur in a very well-known technique that goes back to the 70s, which is called as Factorable Reformulation of MINLPs, proposed by McCormick. So global optimization solvers such as Antigone, Barron, Kuhn, Lindo, Skip, all rely on constructing convex relaxations of MINLPs, which are obtained after performing a factorable reformulation on a given problem, right? So what is this factorable reformulation? So let's suppose you're given an original MINLP that looks as follows. So you have an objective function, which is x1 times x2 squared x3. There are some trigonometric terms, exponential terms, logarithmic, and more terms. Right? Now, the way you would go about reformulating using this factorable reformulation is to essentially introduce additional variables for example, x2 squared, the trigonometric, exponential, and so on, and bring these down into these constraints. The reason you do that is that it's easier to obtain relaxations, convex and concave envelopes of these constraints as opposed to obtaining directly to this polynomial or monomial term over here. Now, once you bring these down to these constraints, now what you have left in the objective function is essentially a multilinear term. So these essentially would show up from reformulating mixed region nonlinear programs using this factorable reformulation. And there are also other applications where you naturally come up with multilinear programs. Right? Okay. Now, how do you go about constructing a polyhedral relaxation for a multi-MLP? The key idea, let's suppose you're given an objective function, which looks as follows, where I'm asking all of the variables to be between 0 and 1. The first step is to kind of introduce new variables to linearize this objective function, right? And what this means is that you recursively, you pick a pair of terms in the objective function. Let's suppose we pick the first monomial in this objective function, x1, x2, x3, x4. Now you randomly pick a pair. Let's suppose you pick x1, x2, introduce a new variable x6. And now, so x6 essentially represents the product of x1, x2. And now you replace x1, x2 by x6, which gives you this new monomial x6, x3, x4. Now you basically pick x6 and x3. You replace that by a new variable x7 and so on. And you end up introducing 3 new variables. Right? Now, with every introduction of a new variable, you reduce the degree of this multilinear term by 1. So eventually you end up with a degree 1 variable, the degree 1 monomial. Right? And this is what we refer to as linearization. So if you do this, so that you reduce a multilinear, an arbitrary degree monomial to a degree 1 monomial, then we say that the particular term has been linearized. So in general, if your monomial has a degree n sub I, then we need n sub I minus 1 additional variables. And so now you could repeat the same procedure for all other multilinear terms, right? So in this case, if you look at x2, x3, you have not seen this before. So you would introduce a new variable x9 and then add x9, x4 to introduce a new variable x10. Now, in the case of x1, x2, x5, for example, you've already introduced x1, x2 to be a new variable x6. So you reuse that variable. And now essentially you would only have to linearize x6, x5 by introducing a new variable x13. Now, what this ends up doing is that you have the original MLP with this polynomial function, just the sum of monomials. And now you convert that into a program where the objective function is all linear and the constraints are now all quadratic, right? So you're not made any change to the original problem in the sense that the minimizers of the MLP also correspond to minimizers of this quadratically constrained program and vice versa, right? So these two are equivalent in terms of local optima, global minima, and so on and so forth. But the reason you do this is the following. So given this bilinear term, xi, xj, now if you want to look at constructing convex envelopes, we essentially have analytical expressions for obtaining the tightest convex underestimator of this bilinear term over this box. And we also have analytical expressions for the tightest concave overestimator for this particular bilinear term over the same box. And so given this non-convex set defined by this quadratic constraint, we can essentially replace that by the convex hull of this quadratic constraint. And that will now consist of these variables xi, xj, xk satisfying these 4 inequalities. So now essentially we have a way of converting the non-convex quadratic constraint and replacing that using a convex hull of that non-convex set. And once you're able to do that, now you have your quadratically constrained problem that we obtained from this MLP. Now we apply this convex and concave envelopes, and essentially we obtain, those are essentially the McCormick inequalities corresponding to the bilinear terms. And you replace the quadratic constraints with the set of inequalities that are defining this convex hull for each of those products. And now you essentially have a valid linear programming relaxation of the original MLP. And as I said, This is a standard technique that's used in a lot of popular global optimization solvers, in particular, for example, BAR. Now, given that you're doing this linearization, right, it turns out there is not just one way to do this linearization. Okay? I can do multiple ways of doing the linearization. So the standard way, that's, for example, the way that's implemented in this popular solver, Baron, is the following that's called as a sequential linearization. So what the sequential linearization does is to first pick a monomial at random, right? Let's suppose we pick the first monomial, and then it just sequentially goes through the order in which the variables have been provided, right? So it goes through x1, x2, gives x6. Now, once you replace the product with x6, you have x6, x3, x4, and now you replace x6, x3 with x7, and x4, x8, and so on. So it just scans a particular monomial left to right and replaces a given leading product in that multilinear term by a new variable and just proceeds. And now if you take the next monomial, it essentially looks at those pairs that have been already introduced. If they have not been introduced, then introduce a new variable, and so on and so forth, until you end up linearizing all of the terms that you have in your objective function. And that essentially, in this particular case, ends up introducing 10 additional variables. Right. Now, I could also do it in a different way, right? Let's, instead of doing a sequential linearization, what I would do, what I call a pairwise. Essentially, I would pick the first pair and introduce a new variable. I will pick a next pair and then introduce a new variable, right? So in the first case, I have a degree 4 term. And so x1, x2 is replaced by x6, x3, x4 replaced by x7. Now x6, x7 is replaced by x8. Now, as I said, this is a degree 4 term. You need 3 additional variables. And so you also need 3 additional variables in this pairwise linearization, just as additional variables represent different products in these two linearizations. Now, if you continue doing the same thing for the rest of the terms, it actually turns out that you only need 9 extra variables to completely linearize all of the terms. So there is not a unique way of performing the linearization. Okay, that's the first. The second, depending on the choice of ordering and the linearization that you do, you could essentially end up with different number of introduced variables. And hence, the LP relaxation would have a different problem size. And that LP relaxation is what you use inside of a branch and bound tree for globally optimizing a MINLP or MLP. And that would now have an effect on how what the computational time for processing the nodes of the branch and bound tree are. So given that you have these two, right? Now, the question that we really wanted to address, and this is questions that have not been addressed in prior work, is how can we obtain a linearization, for example, that leads to the smallest number of introduced variables? Okay, that's the first question that we want to address. And once we have a handle on obtaining such a linearization, then we wanted to study what are the benefits of using such a linearization. So in a sense that what is the root node gap and how effective can a global optimization solver leverage this linearization to basically obtain the optimal solution? Does it reduce the total computational time of the branch and bound process and so on? Okay. So I think it's a good time to maybe stop and see if you have any questions. And Andre, if there are any questions, I can't see the chat, so you may have to help me if there are any questions.
Absolutely. There are no questions.
Okay, all right.
I actually have a question.
Sure.
So just to understand, what happens when you different linearizations? Do you also get different? You're gonna get different polyhedra also, right? So you can have different polyhedral envelopes of the set. And
exactly.
Right. And so having less variables doesn't necessarily imply that you're going to have tighter polyhedra. Is there a result like that?
We actually we can't. There's no one way or the other. I think it's all over the place, right? In fact, some of the results will show you that there is essentially a spread of root node bounds that you can get for the same sized relaxation.
Got it. Got it. Great.
So you will see in the later slides.
I'm excited.
Okay. So as a first step, right? Okay, the sequential linearization, as I said, was a popular technique. In fact, it's implemented in this commercial solvent baron. We want to see if there's a heuristic that we can come up with that can improve on the sequential linearization. And this is the greedy heuristic. Right? And what we are going to do is actually construct a table where the columns represent all of the monomials that we have. And the rows correspond to all the possible pairwise terms that figure in any of the monomials, right? So the set of pairwise terms are x1, x2, x1, x3, x1, x4, x2, x3, x2, x4, x3, x4. So all of these are terms that figure in the first monomial. Now x3, x5, for example, figures only in this monomial. All of the pairwise terms in this monomial are already present in this one. Now, again, over here, you get x1, x5, and then you get x2, x5 that figures in this one, and x4, x5 that figures in the last one. And now what I'm going to do is to count the frequency of occurrence of this pairwise terms in all of the monomials. So x1, x2 figures in the first monomial. It also figures in the fourth monomial over here. So the total occurrence frequency is 2. And you do this for every one of these pairwise terms. x3, x4, it turns out, occurs 3 times in the first one, the second one, and in the third one. And now I'm going to use a simple greedy heuristic. Essentially, I'm going to pick that particular pairwise term that's going to occur most frequently among these monomials. So I'm going to use this, and I'm going to linearize this and introduce a new variable x6 to represent this product. Just as before, once I have done this, I'm going to replace x3, x4 all over by x6, and I'm going to now update my columns, given that I've introduced this new variable x6. I'm also going to update my rows, given that some of these existing products don't really make sense. Right? So now you have x1, x6, x2, x6, and x1, x2 being the possible pairwise products for the first term, and so on. Now recompute the frequencies of occurrence of all of these. And now it turns out x1, x2, x2, x6, and x1, x5 occur with a frequency of 2. I'm going to just break the tie at random and set x1, x2 to be equal to new variable x1, x7. And then you essentially update the table again, and you go on. And now it turns out that you need just 8 extra variables in order to linearize this objective function. So clearly, we started with the sequential linearization, that's the standard one that is used. So you get about 10 introduced variables in that case. Now, if you do this pairwise linearization, then you get 9. Now, with the greedy heuristic, we can actually reduce it by a further variable and get 8 introduced variables. So the next question that we wanted to address is, can we find a smaller linearization for this example? And in particular, can we find the smallest possible linearization? That, in a sense, what I'm asking for is that linearization in which the number of additional variables is the smallest. So in order to define the linearization, right, I'm going to use the concept of an in-tree. Okay? So an in-tree is essentially a rooted tree in which all the arcs are directed towards the root. Now consider the monomial, right? Following monomial, where S sub I represents the subset of the variables xj that actually figure in that monomial. The in-tree has the following properties. So the root node corresponds to the monomial. So in this particular case, you have x1, x2, x3, x4, and x1, x2, and now I'm going to represent 2 child nodes, x1 and x2, x3, x4. Now for x2, x3, x4, I'm going to have 2 child nodes, so x2 and x3, x4. And for x3, x4, I'm going to have 2 further children nodes, x3 and x1. And this in-trees that we construct will have the following properties: that the leaf nodes essentially correspond to the individual variables, x1, x2, x3, and x4. The nodes other than the leaf nodes have exactly 2 children, right? Each of which represents a monomial. The product of the monomials represented by child nodes will be equal to the monomial represented by the parent node, right? So essentially you have x3, x4, the parent is x3, x4. Now you x2 times this, and then you get x2, x3, x4, and you have x1 times this, and you get the original monomial. So this essentially is your sequential linearization. Now the pairwise linearization corresponds to the following in-tree, where you take x1 or x2, you form x1, x2, you take x3, x4, you form x3, x4, and then you combine these two to essentially form the monomial that you have. So essentially, I mean, what I'm going to ask for, right? I mean, I'm going to call these two arcs, okay, which have this following property that they represent two monomials, and then the parent is essentially the product of the monomials. So I'm going to call such arcs to be hyperarcs. Right? And a linearization is essentially a subset of an hyperarcs, with such that the induced graph is an int, right? I'm going to show you what this big graph looks like. And this big, what we'll now do is to use a Dacian diagram or a dynamic programming property to construct all the possible linearizations, actually encode all the possible linearizations in a big graph. And that is, next few slides will show you how you can do that. So as you have seen in all of this talks over the last 3 days, is that you're in a Dacian diagram, right? You have the stage-wise structure, you have this DP structure. So you have layers, and I'm going to basically, each of these layers essentially correspond to the possible monomial terms of degree 1, degree 2, degree 3, and degree 4. Right? So these are all the possible terms, all possible monomials, which I will call intermediate monomials that you can form using the variables that figure in that particular multilinear term. Right? So degree 1 would essentially be the individual variables that figure in that multilinear term. Now layer 2 would figure out all the pairwise products, layer 3, all the triples, and finally degree 4 turns out to be the monomial that you have. And now I'm going to actually add these hyperarcs, which essentially correspond to these children whose product would essentially correspond to the monomial represented by the parent, the head of the arc. Right? So the two tails corresponds to the two monomials, and the head of those two arcs, I'm going to call the pair of these arcs to be in hyperarc, and essentially the head of this hyperarc would essentially correspond to the intermediate monomial that is formed by taking the product of these two terms. And so now for the first layer, you're essentially going to take the individual variables and you're going to form degree 2 terms. So x1 and x2, and you have this hyperarc that gives you this node corresponds to x1, x2, similarly for x1, x3, and so on. And now if you go to a third degree, you can form that using x1, x2, and then with x1. You can also form that with x2 times x1, x3. And so there are 3 different ways. There are 3 hyperarcs that are essentially incident on this particular node.
Arvind?
And you can complete essentially product. Sorry, yes.
Sorry, there's a quick question. I'm sorry if it's okay to interrupt you.
Sure.
Mohsen asked, is it possible to use a hypergraph for this process?
I think you can, it's possible. I mean, the hyperarc is, we are only using it as a possible representation gadget, nothing more than that. Eventually, we will use this to actually translate, use this representation to translate the computation of the smallest linearization into an IP, right? So this is only for purpose of essentially encoding all the possible solutions. And yeah, I think it's possible to use an hypergraph as well.
Thank you.
Can I make a comment or make my question more clear, or
sure,
if you
please,
have time? Okay, so what I meant is that, okay, so you have 4 variables, right?
Yeah.
We can shape a complete graph on these 4 variables, and this could be a hyper edge in a hypergraph, right? So we know that this graph is a representation of a hypergraph. I meant that. So here we have some, we can choose some hyper edges of degree 2, then those would be our monomials of degree 2. We can choose some hyper edges of degree 3, then those could be our monomials of degree 3, something like this. Then for every term in your objective function, we can have different hypergraphs that are represented by graphs, then communicate between them. So then we may be able to have the minimum, possibly minimum number of variables for the whole objective function. I meant this. I don't know if it's possible.
I think that's you're going down the right track. In fact, I think if you let me progress a few more slides, maybe you see this to be exactly what you meant. Right?
Okay.
So I'm using this. No problem. I'm just using this device to essentially explain I'm creating one hypergraph or one relation diagram for each monomial, but you could also create a combined one for all of the monomials in together, right? So to kind of reduce the number of variables and so on and so forth in the eventual formulation.
Okay, thank you. Thank you. Perfect.
Right. Good. Good. Is there another question, Andre?
That's it.
Okay, great, right. So now I have created all the ways that you can form a degree 3 monomial, and finally, for the final layer to basically form the degree 4 monomial, now you could either form that using products of x1, x2, and say x3, x4, or x1, x3, and x2, x4, or you could essentially take a product of a degree 1 and a degree 3, and so on. Right? So there are multiple hyperarcs incident on this particular edge. So this essentially is a complete representation of all the possible ways that you can linearize this monomial term x1, x2, x3, x4. And every entry, as I explained before, every entry in this diagram would essentially correspond to a linearization. And I will show you an example. Say, for example, if you use x1, x2 to form the product x1, x2, now if you add x3, now form the triple x1, x2, x3, and finally the monomial term, you essentially have sequential linearization. And this, as I said, is an entry which is induced by the hyperarcs that you have chosen in this diagram. Now, if you choose a different set of hyperarcs, in this case, this particular one shown in red, you would now come up with the pairwise linearization, right? So essentially, a linearization is choosing a subset of hyperarcs so that the induced graph has an entry. Now, to give you a little bit more insight, so now what we have are a set of nodes in the for the relation diagram, and I've now coded that from 1 to 15. Now, for every node in this, I'm going to essentially associate a degree function, which essentially tells me what is the monomial that is being represented by a particular node. And for this particular node, you're representing x1, so it is 1, 0, 0. So the standard binary encoding 0, 1 vector, indicator vector for each of those monomial terms. The hyperarcs that you have in this, represented by the set hi, essentially have two tails and one head. And a hyperarc exists in this diagram if the sum of the degrees of the tails corresponds to the degree of the head. Right? So those are the hyperarcs, hyper edges that are present in this diagram. And as an example, if you have tail 1 of 1, tail 1 of tail 2 of the first hyperarc, now you sum those two degrees, you essentially get x1, x2, the monomial. And so to construct now to essentially formulate an integer program to represent all the possible encodings and then actually compute the minimum linearization, we are going to now associate a binary variable zin with each of the nodes. So these correspond to each of the intermediate nodes, not the original variables, only for the nodes that are shown in blue. And we also associate a binary variable with respect to all of these arcs and hyperarcs. Essentially, that shows which linearization, or essentially which entry you are picking from this diagram. And as you know, the thing that you will do is we will have a flow constraint. So essentially, if you look at node 11, so we have these two, this hyperarc that is incident on this thing. So there's an incoming hyperarc, and you're going to sum on all the incoming hyperarcs, and now ask for that to be equal to the outgoing hyperarc from the node. So the outgoing hyperarc will only be one. You could have multiple incoming hyperarcs for all these intermediate nodes. And for the last node, you only have incoming hyperarcs, and we essentially require the sum of all the incoming hyperarcs to the last node will essentially sum up to 1. And we have big M constraints that also ensure that if a particular intermediate node, for example, if you have not chosen x1, x2, for example, so in x1, x2, and x3, if you have not chosen x3, it will ensure that you cannot pick this hyperarc, right? Because in order to essentially have this particular term in your linearization, you need to pick both x1, x2, and x3, or you could pick one of the other hyperarcs. Now, if it turns out these two are not picked, then this particular hyperarc can never be chosen in the linearization, for example. So that's the big M constraint that we enforce, and that is now enforced using the node variable that you have. And now you can essentially combine this flow variables and this big constraints. And now we have an IP that encodes all the possible linearizations for this single multilinear term. In fact, it turns out the optimal solution is 3. Like for a single term, you need ni minus 1, so 4 minus 1 additional variables. And it also shows you multiple, you can also enumerate multiple optimal solutions. And there are 15 different ways that you can linearize this particular term, right? A single term is not so important to us. What we really want is to be able to linearize the entire polynomial. And so we would essentially construct now the decision diagrams that I described for each one of these monomial terms. And now you have also the key thing that we want to exploit is commonality between these different multilinear terms. And so the thing that we would do is for looking for common intermediates in all of these diagrams, and you would have linking constraints saying that if you pick this particular intermediate monomial in one diagram, that particular thing is also activated in other diagrams. So it's also available for performing the linearization of the other monomials, right? So this is the way, exactly like Mohsen said, you're creating diagrams for each of these monomials and then kind of linking them together using these linking constraints, given that particular intermediate occurs in both of them, in all of them. And so now you can put together the entire IP for the MLP. So now you have the objective function that you can accurately capture, so that will count the number of intermediate terms that get introduced in the linearization. And then you put in all the constraints that I showed for a single monomial linearization. And then you also have this linking constraints. And finally, the last constraint essentially shows that the outflow from each of those root nodes from each of the diagrams is exactly equal to 1. Now, if you apply that to the particular example that I showed you, that is over here, the optimal solution turns out to be 7. So you just need to introduce 7 additional variables in order to linearize this problem. Okay? So, and you can also, based on the arcs that are chosen, you can actually recover the linearization. And what I'm showing you on the bottom is this particular linearization that only requires 7 additional variables to linearize this monomial. Okay? So in summary, right? So what I started off by showing you is for this particular polynomial, we can essentially do a sequential linearization that introduces 10 variables, a pairwise, which introduces 9, and then you have a greedy heuristic, which gives you 8, and its IP, the minimum linearization, that gives you just 7 introduced variables. Right? So now we have a way of computing the smallest sized relaxation for a given MLP. And now what we want to do is test it out on a bunch of MLP instances. So we actually generated 330 randomly random MLP instances. We chose that the variables just lie between 0 and 1. Now we have generated instances of degree 3 and degree 4. The number of variables go from 20 to 40 in increments of 5. And the number of monomial terms that you have in the objective function goes from 50 to 150 in increments of 10. Now, the indices of each set that you have in the monomial is actually chosen at random. The coefficients are randomly generated from a uniform distribution of -100 to 100. And we implemented the sequential linearization, the heuristic linearization, and an IP linearization, all of them in Julia. And we solved the IP using Gurobi with a time limit of just 5 seconds. Right? And we found at the end of that 5 seconds, we found and stored actually up to 100 optimal solutions. Essentially, if you solve the problem to optimality, Gurobi then spends a little bit more time to actually give you 100 other alternate optimal solutions. Essentially, they will all be minimum linearizations, but they will be different linearizations. And for each linearization, we constructed and solved this LP relaxation, which will correspond to your root node relaxation of the MLP, and then computed the root node lower bound. And now we would essentially compare this polyhedral relaxations for using these different linearizations in terms of the number of variables, the root node optimality gap, where the root node optimality gap is given as follows, where we essentially constructed an upper bound by solving the MLP using a non-convex solver, and use this upper bound to then compute the root node gap. Yeah. So this plot essentially shows you, right, on the top essentially shows you our performance of the heuristic linearization versus the sequential linearization. And the y-axis gives you the reduction in the number of variables, the percentage reduction in the number of variables, and the x-axis gives you the proportion of instances where certain reduction was observed. So essentially, a tiny fraction you can get nearly 30% reduction versus compared to the sequential linearization approach, whereas for about 50% of the instances, you can get about 10% reduction in the number of variables. So it just shows you clearly that doing a different linearization compared to the standard sequential linearization can give you reductions in the size of the linear programming relaxation. Now, if you do the IP, you can clearly see that we can again get a different proportion of instances for which, for example, for 50% of the, for the 40% of the instances, we can get about 15% reduction. So you get a different performance from using the IP versus the heuristic. I may have switched the two plots, I'm sorry. Yeah. So now I will come back and address the question that Andre raised before, right? So Andre raised the question of whether you get different root node bounds corresponding to the same sized linearization. So what I'm going to look at is a plot for a particular instance of degree 3, okay? And the red essentially corresponds to the relaxation bound that you get by using the sequential linearization. The green corresponds to using the root node bound that you get using the heuristic linearization. These blue dots essentially correspond to the 100 different minimum linearizations that I get from Gurobi, right? So I said each one of these dots is the same size linearization, but then it's a different entry in the decision diagrams that you have. And each one of these dots essentially gives you a different LP bound. As you can see, there are certain bounds that do much better than the heuristic. There are a whole lot of whole lot of linearizations, minimum linearizations that actually do worse than what you get with the heuristic. And as I said, the heuristic essentially has more variables than the minimum linearization. And so in our subsequent experiments, what we did was to basically, from these 100 different linearizations that we have from the IP, we basically chose the best one, right? And used that to provide a linearization to BAR. So in the next set of experiments, we are essentially comparing now the root node gap for across the instances, and we are comparing the heuristic versus sequential, right? So it turns out that in some cases, the heuristic actually does worse than the sequential linearization because, as I said, our strategy was tailored to reducing the number of bounds. We actually did not do anything in terms of taking care of the root node relaxation. And as a consequence, it is possible that even though you have reduced the number of variables in the problem, you may end up worsening the root node bound relaxation. And this plot shows you that you actually end up doing that. But there are a substantial number of instances, more than 70% of the instances, where you actually improve the root node bound, right? So the root node gap is much smaller compared to what you would do with the sequential linearization. And in the case of the IP, it turns out to be much better in the sense that there are very few cases where you actually do worse than the sequential. So in most of the cases, you're actually doing better. But remember that I'm using, out of the 100 solutions that Gurobi gave me, I'm using the one that has the best root node bound, and I'm using that for comparison over here. All right. So then we did a second set of experiments. Now is to figure out, okay, now we have a way of computing the minimum linearization, and we know that provides much smaller relaxations compared to the existing state of the art. Now we want to see what is the impact on actually providing that to a global optimization solver. So for each MLP instance that we have, we construct this quadratically constrained program that I showed you before using one of these linearizations. So it could be either the sequential, the greedy, or the IP formulation. We solve each of these QCPs to global optimality with Barron. And the QCPs are essentially provided with the with the reformulations that we have. We have a time limit of 500 seconds. So in these two cases, the time that is required to compute the linearization is really small. So we all the 500 seconds are available for Barron to solve this QCP. Whereas in this case of the IP linearization, we provide 500 minus the time that is required by the IP linearization, and then provide the remaining time for Barron to solve the IP-based linearization QCP. So here's, I think, a performance profile. So we picked out 151 non-trivial MLP instances and solved them as non-convex QCPs with Barron. The first plot here is actually showing the percentage of models that are solved within a particular amount of time. The red line corresponds to Barron sequential. The green corresponds to using the heuristic linearization. And the last one corresponds to using the IP, the minimum linearization coming from the IP formulation that we have. And as you can see, at any given time, the formulation using this minimum linearization clearly ends up solving more percentage of problems to optimality than the other two approaches. This is always above all of this two, this green and the red line. Now, at the end of the 500 seconds, now if you compare the remaining gap at 500 seconds, also we turn out to be doing much better than doing the sequential approach. So clearly, doing this minimum linearization seems to end up providing a benefit of reducing the LP relaxation. And we have an unintended consequence that we are also able to improve the root node bound, and it actually does better in terms of solving the problem. So this is all about solving this minimum linearization, find the smallest size linearization for a given MLP. And for a particular instance, for example, so here's this particular test problem that we have from a test set. If we did the sequential linearization, we get about 297 variables. If you do the heuristic, you get 252. If you do this minimum linearization, we get about 246. So a 17% reduction corresponds to the sequential approach. Now, if you solve the original MLP, you can actually solve it with Barron using 106 seconds. The reason Barron is very fast on this is essentially it can recognize the MLP structure and it actually adds valid inequalities that are tailored to the MLP. But then it does that at the root node, but once it's done adding these valid inequalities, then it actually does the sequential linearization. And then actually, in order to do the branch and bound, it is using this sequential linearization based LP. But the sequential linearization LP plus this valid inequalities actually ends up being very, very efficient for solving this problem. And that is what happens with Barron being able to solve this original MLP within 106 seconds. Now, if you give the sequential QCP, then Barron is not able to solve the problem within 500 seconds. If you do that with a heuristic, Barron can solve it in less than 300 seconds. And if you get the minimum linearization using our formulation, Barron can actually get to 137 seconds. So it's very close to what you do with the original MLP. So what you can do already is that you can essentially replace the LP that Barron has, which is obtained for sequential linearization, with this LP based on the IP formulation, and I'm sure you can already beat this 106 seconds. Now, on the other hand, you give the same linearizations to Gurobi. You can also see that you can go from 39 seconds using the sequential to actually just using 9 seconds for the minimum linearization that we have. All right. So I showed you essentially that this formulation using this minimum linearization, and I showed you that there is possibility that you can actually get benefits by going to a smaller formulation. But like I said, that is only happenstance. We did not do anything rigorously in order to ensure that the bounds were always good. Right? So the next question, the follow-up question that we wanted to address was how can we get tighter linearizations? Right? So our formulation can only identify minimum linearizations. And as we have seen, there are multiple minimum linearizations with varying root node bounds. And our initial objective or motivation for looking at minimum linearization was to get small LP times, right? So that the entire solution of the branching bound algorithm was fast. Now we want to address the question, can we identify the linearization that gives you the best root node bound? Okay. So I'll just give you some intuitions on this. I'm not going to go deep on this. So a linearization that I said is actually choosing a subset of hyperarcs so that you have an induced graph, such that the induced graph is an entry in every one of these relation diagrams representing each one of those monomials. It also is true that if you choose any subset of hyperarcs such that the induced graph has at least one entry, so you can essentially also include additional hyperarcs in that subset, that is also a valid choice, and it would still also represent a linearization for each of those monomials. In fact, this is a generic plot that I'm showing you. Let's suppose this A min is a set of hyperarcs corresponding to a minimum linearization, for example. Now, if you keep adding additional hyperarcs to this set, you can actually show that the root node bound cannot get worse. So, and just keep adding, and you end up adding all the hyperarcs, all the diagrams, you could automatically see that you should get the best possible bound at the LP relaxation. But then that would lead to a lot of inequalities. The question is, we don't need all of them. We need only some of them. And which one should we choose so that we can get as tight as choosing all of the hyperarcs? So that essentially turns out to be a bilevel formulation for identifying the best bound linearization. Essentially, what we want to do is we want to identify a subset of the hyperarcs so that they define a linearization. And we want to maximize over this, right? And what do we want to maximize? We essentially want to maximize the optimal value of the LP relaxation. So once you choose a subset of hyperarcs, then you can essentially define the McCormick's that define the linear programming, the polyhedral relaxation of the MLP, and you get a corresponding LP objective, right? So this essentially is your LP that results from choosing a particular set of hyperarcs, and you essentially minimize this objective, and then you want to essentially maximize over the set of all possible choices of these hyperarcs. And we actually can solve this bilevel problem to optimality by reducing to a one-level MIP, right? And this is something very recent. I'm not going to present a lot of results, but I'm just going to explain what we can do using a simple example, right? So let's suppose we have this example where we have three monomial terms, and all of them are degree 3. And I'm showing you this full, and like Mohsen mentioned, that I'm showing you now a hypergraph where I have essentially intersected the arcs and the nodes across all of these monomial terms, right? And I'm showing you a single Bayesian diagram, which essentially where the roots are now, you have multiple roots, not single root, and each of these roots essentially correspond to the different monomials that you have in the objective function. Now, if you choose all of the hyperarcs and then produce an LP relaxation, it turns out you'll have 13 variables in the LP, 45 constraints, and you'll achieve a root node objective of -1, right? So any other linearization that you produce cannot get better than this, right? So this -1 is essentially the best that you can get using McCormick inequalities to linearize this MLP. Now, if you do a sequential linearization, then it turns out you can use 10 variables, you introduce 18 constraints, and you get a root node objective of -4/3. So it's clearly worse than choosing all of the hyperarcs. Now, if I pick a minimum linearization, right, then the LP, for example, has 9 variables, 15 constraints, and the root node objective is still -4/3. Now, if we use our formulation for the best bound linearization, we are able to solve this bilevel formulation. So if we actually solve this bilevel formulation, then we can actually produce a best minimum linearization, which has 9 variables, 15 constraints, just like this one, but can produce a root node objective of -1. So what I showed you till now was just the minimum linearization, and then we're just enumerating solutions and picking the best one. Now what I can do is essentially solve a bilevel optimization problem and directly give you the best bound relaxation for a given number of inequalities that you want in the relaxation. So if you say if you want no more than say 15 constraints in the LP relaxation for the MLP, I can then give you that particular linearization that gives you the best bound, given you can only include 15 constraints. Now, if you give me 18 or 20, clearly I can do better than what I can do for 15, but not in this particular case. But essentially, I can do this for a constrained budget, right? So you tell me you don't want to have more than these many McCormick inequalities in your LP relaxation, and then I can give you the best possible linearization for that. This is still, this is more recent results, so I'm not giving you more details, but we are fairly confident that we can do this. And hopefully in a future talk, I can give you more information. Thanks very much for listening to this, and I'll be happy to take questions.
Thanks so much, Arvind, for the excellent talk. Does anybody have any questions? So while people think about their questions,
yes,
I even sent you by email some references, but what I have seen before is that some people, at least they try to find facets of the strongest possible polyhedron, the tightest possible. I wonder, maybe even solving this MIP, single level MIP after reformulation, because the graph can be large, right? Depending on the size, it could be expensive. Are you also considering maybe just finding some inequalities, maybe from the projection of this network? Because I believe it's going to be a big flow model as well, right? Maybe you can get facet defined inequalities from the projection of the polyhedron to get at least facets or something.
That's a very good idea. We have not really explored. I mean, this is just initial, I think when we first posed the bilevel problem, we were not even sure we could actually solve the problem, right? And it's only recently that I think we were able to figure out that we can actually reduce that to a single level MIP that you can essentially give that to Gurobi and get a solution, right? So, and I think there is work, I think the work that you're referring to is by Jim Lutke, Linderoth, and I think their student, I think, where I think they were able to characterize a lot of, I mean, maybe even the convex hull of the MLP and facet defining inequalities. And Barron, for example, uses these inequalities and adds these inequalities, but the base, right, it still needs an LP relaxation finally once it starts branching. Right. So there's still a reformulation based on the linearization that I mentioned to actually do the branch and bound algorithm. And these valid inequalities essentially lie on top of that.
Got it. Got it.
And so I think what we do would still benefit the entire solution process, regardless. So what we do could essentially be considered as a pre-processing step that you do before you start solving the MLP. Just like you're adding this, computing this cuts, you can also essentially compute one of these linearizations. And yes, right now it turns out to be fairly big, right? I think because if you're considering all the possible hyperarcs or all the diagrams, so it does turn out to be a huge IP. But when we end up essentially doing just a heuristic search with a budget like 5 seconds or like a 30-second budget, right? So we don't even care about actually solving it to optimality, just kind of trying to improve on a heuristic and so on and so forth, right? And then you can just stop at this point. I mean, we're just showing you, yes, we can solve it to optimality, but you could pretty much use this as a pre-processing step before you solve the MLP. And the idea that you're saying about projections and finding valid inequalities are some things to be considered in the future. That's definitely a avenue to consider in the future.
We also have a question from Mateus. Mateus, do you want to ask yourself? But I can read. The problem of minimizing the number of introduced variables is hard. So is that NP hard to find the minimum number of introduced variables?
It is actually that is a part that I've not shown, and that is a part I think is attributable all to Carlos Cordonía. I think he was able to show that this problem of minimizing number of additional variables can be reduced from the I think Dominique said problem. I think Carlos, correct me if I'm wrong.
Yeah, no, I can talk very quickly.
Sure.
So yeah, you are right, and the proof is actually convoluted, so to say. So we at the same time show that a special case of the problem is NP hard, and we also show that it's fixed parameter tractable actually. But bottom line is that the problem is hard and the reduction follows from the dominating set problem.
Okay, thanks.
Any more questions?
Hello, sir. So there is a lot of degeneracy if we see that we got 100 different optimal solution in the slide 42 where you have discussed. So is there a way, like if we in the standard optimization, like in Bender's cut, when we add, we get a lot of degenerate solution. And then there's a Magnanti and Wong, they have suggested another problem you solve and you get a best solution, which will give the tightest cut. So can we have something like here, we have out of 100 optimal solution, can we write another problem rather than evaluating all the 100 and find the best out of this?
And that's also a valid avenue for exploration, right? I mean, you can definitely do that. But when we also thought about the same thing about how do we go about finding the best among a given sized linearization, and that's essentially what we are doing with this bilevel problem, right? So usually, I think what we are doing here is essentially we are limiting the number of hyperarcs that are chosen, and that essentially will tell you the number of additional variables that you can have in the problem, right? It's like it's not the exact thing, but it's essentially a pseudo for the number of additional variables that you end up introducing in the problem, and you can use that to budget the number of inequalities that you'd have in the LP relaxation, and then find among all possible such linearizations, you find the best one. So we could essentially solve this directly without having to do this two different problems. So we can show that we can actually reformulate this bilevel problem to a single level MIP. Right? And you can just throw this to Gurobi, you can throw this to any solver that you like. And then that will automatically give you the optimal solution, essentially already identify, for example, in this particular case, if this is the best that you can do, it will automatically end up identifying this particular linearization. So you don't have to do this, find first the minimum linearization and then do something else like Magnati and more.
Thank you.
All right, we have another question from Alia Alnagar. Is it always the case that fewer variables improve computational efficiency? How do the top two problems in slide 50 with the same root node objective compare computationally? So let's go to the first. Yeah.
Yeah. So, I mean, in general, I think so. For example, if you take polynomial complexity with interior point methods, then I think there's a direct relation to the number of variables and constraints that you have in the problem, right? I mean, there's also this issue of sparsity because that involves in the factorization. So, as we go with interior point methods, the polynomial, the complexity of in terms of number of iterations scales directly with the number of variables and constraints. So having smaller size problem gives you efficiency. Now you said active set methods and simplex methods, it's not really clear, but I think having fewer constraints essentially implies as a worst case, right? Then you have the concept of this worst case complexity. The worst case complexity would definitely be better if you have fewer number of constraints than the other. So in general, it's only a rule of thumb that a smaller size problem, you should expect to get computational benefits by having having a small size problem. Right. And so was there a second question, Andre?
Yes, there are two more questions. How do the top two problems in slide 50 with the same root nodes objective compare computationally?
I mean, computationally, I mean, I've done a lot more. So for example, in general, the LP, so solve the root node LP, right? Of this versus this, essentially, you get a 100x improvement.
Mm-hmm.
Right? So this essentially turns out to be fairly a dense problem. So here's where I think sparsity actually matters. It turns out that every variable gets involved in some constraints with another set of variables. And so the entire resulting LP with all the possible constraints and variables turns out to be a very dense formulation. So computing this root node graph of -1 would turn out to be computationally more intensive than using one of this formulation, for example. And I've seen that using a larger size MLPs, and it usually turns out an 100x difference between these two.
Great. We have another question from Mohsen Nafar. Have you checked whether there is a relation between the best minimum linearization and the pairwise intersection of the hyperedges of the corresponding hypergraph?
So I think when he says the best minimum linearization in terms of the root node, right? I think so. It turns out that it's not just that. I mean, it's not just picking up some intersection edges, but I think it seems to. I mean, the role of the coefficients play a critical role in which hyper edges that you have to pick in order to get the best root node bound. Right? Mm-hmm. So in this particular case, for example, you actually end up linearizing x1, x3 first, right? And the reason you end up use x1, x3 is because x1, x3 figures in a term that has some positive coefficient, and x1, x3 here figures a term that has a negative coefficient. Right? As I said, the problem is all in constraint, right? So if, for example, if all of the coefficients were of one sign, right? If all of the coefficients are positive, then you would send all the variables to 0. If all of the coefficients were negative, you send all of the variables to 1. So you would automatically get the best possible relaxation at the LP, and it actually turned out to be the optimal value. It's only when the sign changes, right? Then you start to have a conflict. And now, by choosing x1, x3 that shows up in a term that has a positive coefficient and a negative coefficient, you're kind of figuring out the tension that's there between choosing a particular linearization correctly. And that turns out essentially to help you get the best root node bound. And that is what is missing in this other linearizations that you have. Right? In all of the linearization, you end up doing x1, x2, and that essentially ends up doing this. And then there's no commonality. And over here, you end up doing either x3, x4, but then they both have the same sign. And that, in turn, I think you lose the conflict that you have between these two terms. And that causes a loss in tightness. That's our insight into this problem.
All right, so we are right on time. I don't see any questions at this moment. So let's all thanks Arvind very much for this amazing work. It's fantastic, Arvind. I even sent you some things that I saw in the past. I hope that's okay. Maybe you haven't seen before. And let's take a break. The next one is going to be by a great Carlos Cardoña, the great theoretician in our group. So let's take a break. 11:15, we are back. And again, thanks so much, Arvind, for the excellent talk.